Following lecture will cover sections 3.4 to 3.5. In the beginning of chapter 3, we saw how we could use the pKa table to quantify relative acidity. By comparing the pKa values of two acids, we saw that the compound with the higher pKa value was less acidic. In this section, we're going to look at structural features that allow us to compare relative acidity. And there's a system. In the textbook, it outlines the ARIO system, and we're going to go through each of these points and see how we can look at structural features to compare acidity. So, the most important concept here is that when we compare structures, we're going to be converting everything to the conjugate base and comparing conjugate base stability. So our important concept is the stronger the acid, the more stable its conjugate base will be. So as we compare conjugate bases, the one that's more stable will have resulted from the stronger of the two acids. So again, if we look at the stability of a lone pair of electrons on a conjugate base, right, take your original acid, remove the proton, and we're going to be looking at our conjugate base. If the conjugate base is stable, then the acid was stronger. So formal charge is very important here. Formal charges will affect the stability. The more effectively a conjugate base can stabilize that formal charge, the stronger the acid. That's the key concept that will underscore each of the points that we make as we compare acidity from a qualitative perspective. The factors that affect the relative stability of a negative formal charge are the atom, resonance, induction, and the type of orbital. So that's our ARIO system: atom, resonance, induction, and orbital. And we'll be looking at each of these factors separately, and then we'll put it all together. So first, let's begin with the type of atom that the negative charge is on. This is all about the type of atom that the negative formal charge is on. So first, let's look at the group trend. If two elements happen to be in the same group, the larger the atom, the more stable the negative charge. So here's our group trend right here. Let's focus on this box. As you move down a group, atoms get larger. They're more polarizable. The electron clouds are more easily distorted and able to stabilize a negative formal charge. So as we go down a group, the ones lower to the bottom will be more stable conjugate bases that have resulted from more acidic compounds. The period trend is based on electronegativity instead of size, like their group trend. So the period trend, as we move across a group, the more electronegative atom will more easily be able to stabilize the negative charge. Remember, it's all about the atom that has the negative charge after we remove the proton, because we're always comparing the stability of the conjugate bases to compare relative acidity. Let's look at an example. If we want to determine which of the compounds below is more acidic, our first step is we're going to deprotonate. We're going to take off our protons, deprotonate, and determine which will more likely stabilize the negative charge. So we take the protons off. We have a negative charge on carbon versus a negative charge on oxygen. Now, when we have a negative charge on different atoms, carbon is different than oxygen, we're going to be using the atom factor. So which of these atoms can more easily stabilize a negative charge? Well, let's look. Is carbon and oxygen in the same group or the same period? Carbon and oxygen are in the same period on the periodic table, so our deciding factor will be electronegativity. Oxygen is more electronegative than carbon, so this is going to be our more stable conjugate base, meaning propanol was the more acidic proton, or the more acidic compound. So why don't you give this one a shot, pause the video, and try these next two problems. And when you come back, I'll give you the answers. All right, hopefully you were able to give these a shot. Okay, remember, we're going to be applying the atom factor. So we want to determine which compound is more acidic. So what we need to do is deprotonate and we get all right. Now let's ask, is oxygen and sulfur in the same group or same period? They're in the same group on the periodic table. So if we're dealing with the group trend, whichever one is larger or further down on the group, sulfur is a larger atom, so that makes it a more stable conjugate base. And the more stable the conjugate base, the stronger the acid. So H2S is a stronger acid, and H2O is a weaker acid. Because OH minus is a less stable conjugate base. All right, sometimes we'll be comparing protons that are not on the same, not on different molecules. They could be on the same compound. So we're going to be comparing the hydrogen on the nitrogen and the hydrogen on the oxygen. So first step is to deprotonate. And now let's compare these negative charges. I have a negative charge on a nitrogen versus an oxygen. Nitrogen and oxygen are in the same period. So we're going to apply the period trend. So oxygen is more electronegative. Nitrogen is less electronegative. So since oxygen is more electronegative, it can more easily stabilize that negative formal charge, making it more stable. The more stable the conjugate base, the stronger its conjugate acid. So this is the more acidic proton, and this is your less acidic proton. So if we want to check, again, you could always check with your pKa values. H2S has a lower pKa, H2O has a higher pKa. And again, just reiterating in the same problem, it's the electronegativity being the major factor here. All right, the second factor in the ARIO system is resonance. So, what does resonance have to do with formal charges and their stability? Well, resonance can stabilize a formal charge by spreading it out over multiple atoms, resulting in partial charges. So, for example, if we want to compare two compounds, ethanol and acetic acid, and determine which is more acidic, we're going to go through the same process. We're going to deprotonate, get rid of the proton, And now we can compare the stability of the conjugate base. So if you notice, we can't use our atom argument because the negative charge is on identical atoms. It's on an oxygen in both cases. So in this instance, we'd move to our resonance factor and compare. The negative formal charge that came from ethanol, right, we don't see any of our resonance patterns. So there's no resonance possible here. Right, however, we do see with acetic acids, the acetate ion here, we do see one of our patterns. We have an allylic positive charge, an allylic lone pair. So those electrons can move to give us a second resonance structure. And that delocalization can stabilize that formal charge by spreading it out over multiple atoms, making it a more stable compound. So the more stable the conjugate base, the more acidic its conjugate acid. All right, so why don't you give this one a shot? Assess which of the two protons is more acidic. Remember, you need to deprotonate them and then compare. Pause the video. When you come back, I'll give you the answer. All right, hopefully you were able to give this a shot. Okay, so let's take a look at the answer. Now, we first draw the conjugate bases of each of our possible acidic hydrogens here. So the first one, we have the following conjugate base, and our second, removing the second proton, gives us this structure here. All right, so if you notice, we have a negative formal charge on both carbon atoms, so we can't use the atom argument. We move next to resonance. So if we look here, there aren't any of our resonance patterns. That's a localized anion. There are no resonance patterns here. So removing this proton to give the following conjugate base will not result in any resonance structures. There's no resonance stabilization. However, the second proton gives us the allylic lone pair pattern. And we know to push the arrows for this pattern. We get our second resonance structure here. So removing this proton results in a formal charge that can be resonance stabilized. So that means that this conjugate base is more stable, making this top proton the more acidic one. The next factor is called induction. And we've heard the word induction in chapter 1 when we were talking about polarity and how electronegative groups can pull electron density through a bond system, making a bond or a molecule polar. So again, induction is a result of electron withdrawing groups withdrawing electron density, and the effect on a negative formal charge is that it can stabilize a negative formal charge. So electronegative groups that can result in inductive effects are halogens. They are electron withdrawing. Now there's lots of other electron withdrawing groups, however, we're going to focus on the halogens here. So let's look at our example below, where we see an increase in the electronegativity resulting in an increase in the electron withdrawing capability, making our conjugate bases more stable. So we have an acidic proton with no electron withdrawing groups. Call it electron when we move to the next molecule, we have an iodine. So that iodine can stabilize. Imagine you deprotonate that and we get a negative charge. That iodine is slightly electron withdrawing, and it can help to stabilize that negative charge in addition to the resonance stabilization from the carboxylate ion that results. So as we move across, we see an even more acidic compound is one that has a bromine. Bromine is more electron withdrawing than iodine was. It can more easily stabilize that negative charge. Moving across, we have a chlorine, which is more electronegative, creating a more acidic compound, able to more easily stabilize that negative charge. And then as we add even stronger electron withdrawing groups, fluorine, we have a more acidic compound. Now, if you notice, these halogens are on atoms that are, we have 1, 2, there are 3 atoms away from the negative charge. So this inductive effect is basically pulling electron density through that sigma bond framework. Now, the further away the electron withdrawing group gets, obviously the weaker the inductive effect, and the closer it is, the stronger the inductive effect. All right, the next concept is as we add electron withdrawing groups, we increase the stability of the conjugate bases. So let's take a look at our first compound. There are no electron withdrawing groups. When we add 1 chlorine, it becomes more acidic. 2 chlorines, even more acidic. And if you add 3 chlorine atoms, it greatly increases the acidity. The next concept is the closer the electron withdrawing group, the more stable the conjugate base. So if you look, the bromine is 1, 2, 3, 4, 5 atoms away from that negative charge if we were to deprotonate. Then we get the bromine that's closer, right? The inductive effects will be stronger, resulting in a more stable conjugate base, increasing the acidity of the conjugate acid. And then when a bromine is even closer, we see we have an even more acidic compound. Let's take a look at an example here. Which of the following protons is more acidic? So let's compare our 2 protons. We're going to deprotonate and we'll compare them separately. So let's look at the first one. We end up with a negative charge on the oxygen. And when we deprotonate the second one, we also end up with a negative charge on the oxygen. So in this case, we have negative formal charges on the same atom. The atom argument, that A factor, we can't apply. We can't apply the resonance factor because there are no resonance patterns, so there's no additional resonance structures that can be drawn for either of these formal charges. So we move on to the induction factor. And what we're looking for is, are there any electron withdrawing groups in the vicinity of our negative formal charge? And yes, there are. We have 2 carbons, that's 1, 2, 3 atoms away, that has electron withdrawing fluorine atoms. So if we compare that negative formal charge to the one on the right, this one is going to be more stable. And the more stable the conjugate base, the stronger its conjugate acid. So this would be your stronger or more acidic proton. All right, why don't you try the next example? Rank the acidity of the compounds below. So pause the video, look at the structures, and apply what you know about induction and rank them in terms of their acidity. Okay, so in ranking the acidity of these compounds, we're going to look for any inductive effects, and we're going to consider the electronegativity of the adjacent atoms. So we see no electron withdrawing groups. There are no halogens attached. We see some halogens on compounds 1, 3, and 4. So it looks like compound 2 will be the least acidic because compound 2, when we deprotonate it, there are no inductive effects to stabilize that negative charge. Now let's compare the other ones. So if you see compound 1 has 2 fluorine atoms, and fluorine is the most electronegative atom, and there's 2 of them. So that's likely to be the most acidic because it will have the greatest inductive effects to stabilize the negative formal charge if we were to deprotonate that. And then comparing chlorine and bromine, chlorine is more electronegative than bromine, so compound 3 is next, and then compound 4. The next factor that we consider when qualitatively assessing relative acidity is the type of orbital that the negative formal charge, right, or the lone pair of electrons will be in. So the more closely the electrons are held to the nucleus, the more stable they are. So sp3 orbitals are further away from the nucleus than sp2, and sp orbitals are held most closely to the nucleus. Therefore, electrons in an sp hybrid orbital will be more stable. So the ability to stabilize a charge, sp is the greatest. Sp hybridizations will give more acidic compounds, sp3, least acidic. And let's take a look. We have all sp3, all these hydrogens are attached to a carbon that is sp3 hybridized. These are the least acidic. And we have our sp2, our proton that's on an sp2 hybrid carbon. It's a slightly more acidic. If you look at the pKa value, it's getting a little bit lower. And then now if we look at an sp hybridized carbon that has a hydrogen attached, right, when we remove or deprotonate that and we're left with a negative formal charge on that carbon, that sp hybrid orbital can more easily stabilize that negative charge because, as we said before, the electrons are held more closely to the nucleus. See how the pKa value here has gone down? So if we look at an example, we want to decide which proton is more acidic. Just like every single example, we have to deprotonate and compare the stability of the conjugate base. So let's first look at our lone pair that happens to be on an sp2 hybridized carbon versus when we deprotonate the second proton, our lone pair is on an sp hybrid carbon, so that sp hybridized carbon can more easily stabilize that negative charge. The more stable the conjugate base, the more acidic its conjugate acid. So we have our more acidic proton and our less acidic proton. All right, so when we rank the factors, we put them in the order that we learned them, A, R, I, then O, and we move through them in that order if we're dealing with compounds that have multiple factors working. let's look at a couple examples. We want to compare ethanol and propylene. Let's determine which has a more stable conjugate base and which ultimately would be more acidic. So we deprotonate. We have oxygen and carbon with a negative charge. So it looks like we can use our atom argument. We have oxygen versus carbon. They're in the same period, so we use electronegativity. So our atom argument, oxygen is more electronegative. But if you notice, our carbon here, right, that's an allylic lone pair, so we do have resonance stabilization. However, factor 1 beats factor 2. So ethanol is going to be more acidic. The point is that we're using our factors in order, right? They both have a factor that increases the stability. However, when we rank them in order, we see that the atom factor beats the resonance factor, and it allows us to assign which compound is more acidic and which conjugate base was more stable. All right, so if we want to compare the acidity of our two protons here, we have to deprotonate. So if we deprotonate the one on the left, we get the following conjugate base. If we deprotonate the one on the right, separately, we get the conjugate base on the right. So it looks like on the left here, and on the right, we have an atom, so we can't use the atom argument. Let's move to resonance. So the following compound is resonance stabilized because we have an allylic lone pair. There's no resonance on the one on the right. All right, however, the one on the right does have induction. And there is no induction here. So, remember, we rank them in order. So resonance beats induction. Therefore, our proton on the left is more acidic. All right, I'd like you to try this one. You can pause the video and rank the following protons in terms of their acidity. All right, let's take a look at the answer. For each of the molecules, or for each of the protons below, we're going to rank them. So let's imagine removing the conjugate, or removing the protons, and we're going to compare the stability of the conjugate bases. So I'm going to draw a molecule with all three protons off. Okay, let's go through the order. Let's start with our atom argument. Well, it looks like I've got a negative charge on 2 nitrogen and an oxygen. So for the atom argument, this oxygen has the most stable lone pair, or formal charge. So we can put this proton as most acidic right away. Now we have to compare these two. Let's move to our R. So our formal charge on the top does not have a resonance pattern. However, here we see that we have a lone pair that's allylic to our double bond here, so there is resonance. So that means that HB, this proton, will be next in line, rendering HC the least acidic. All right, moving along to section 3.5. Now that we know the ARIO system to compare relative acidity, we can use this to predict the position of an equilibrium. Now, if you remember, in section 3.3, yeah, 3.3 or 3.4, we were using our pKa tables to do this and assigning the pKa values to the acids on both sides, right? The higher pKa value was the weaker acid, and the equilibrium always favors the formation of the weaker acid and weaker base. So that was our first method. Our second method is to do this without pKa values, and we're going to compare the relative stability of the conjugate bases. So we know that the equilibrium favors the side with the weaker acid and weaker base. So here, this is the key. We're going to look for the most stable conjugate base. That will be your weaker base. The equilibrium will favor the weaker base or the most stable conjugate base. So all we're looking at is our conjugate bases. Whichever one happens to be more stable, that's where the equilibrium lies. So if A was more stable, the equilibrium would lie to the right. If B was more stable, the equilibrium would lie to the left. Let's look at an example. We're going to use our ARIO system to compare the stability of the conjugate bases. That's all you have to do is look at the conjugate bases. We've got, and we're going to go through the ARIO system. Let's start with A. We have a negative charge on carbon versus a negative charge on oxygen. Carbon and oxygen are in the same period, so it's an electronegativity effect. Oxygen is more electronegative. Therefore, we have a more stable conjugate base. Therefore, the equilibrium will lie to the right. The equilibrium favors the products. All right, so I'd like you to try these next two problems. You can pause the video. When you come back, I'll give you the answers. All right, so if we're applying the ARIO system, let's compare the conjugate bases only. We see that our atom argument will not work. The atom factor is out because we have a negative charge on identical atoms. Let's move to resonance. Well, I'm not seeing any resonance patterns, so resonance is out. Let's move along to the I factor, induction. We've got some electron withdrawing groups on our carbon 3 atoms away, and there are no electron withdrawing groups on the conjugate base and the reactants. So because our compound and our products is induction stabilized, it will be the more stable conjugate base. And we know the equilibrium favors the more stable conjugate base, more stable of the two conjugate bases, so our equilibrium lies to the right. favoring the products. In our next example, again, we're looking at the conjugate bases only. Let's try our atom argument. We have a negative charge on oxygen versus nitrogen. So right off the bat, using the atom argument, it looks like we have a more stable conjugate base. Also, we have resonance stabilization. So it's more stable due to both factors, but really we can make our decision on our first atom factor. We have a more stable conjugate base in our reactants, so the equilibrium will lie to the left, favoring the reactants. We're moving to section 3.8, counterions. So this is really quick and easy. Counterions are always going to be spectator ions. So let's consider a compound NaNH2. All right, Na is the counter ion. All right, it's counter to the negative charge. They're just there to balance the charge, but they're not reactive. So if we were to look at a full reaction with the counter ion included, we see that our counter ions are just there to balance a negative charge. Typically, we're going to see counter ions being our group 1 metal ions, and they are spectators. So we really don't need to write them in. You can write the reaction without the counter ions. So don't worry when you see these group 1 metal atoms. They're spectator ions. They don't participate in the reaction other than to just balance the overall charge of the solution. And finally, in our last section here, we're going to look at Lewis acids and Lewis bases. Lewis acid-base theory is different than Bronsted acid-base theory. Bronsted-Lowry acids are proton donors. Bronsted-Lowry bases are proton acceptors. With Lewis acids and bases, it's not protons, we're talking about electron pairs. So Lewis acids accept electron pairs, Lewis bases donate electron pairs. So if you're looking at a set of reactants, the compound that has the lone pair will be your Lewis base because it can donate them. Boron and a lot of metals are typically going to be your Lewis acids because they like to accept electron pairs. So another example would be something like NH3. Nitrogen-containing compounds are very often Lewis bases as well. And this would be the complex that's formed between water and BF3. So, if you see this on a test, a quick and easy way to remember what the Lewis acids and bases are, just look for the boron-containing compound. If you see boron, it's always a Lewis acid. If you see nitrogen or oxygen, it's always the Lewis base.